So we have Oliver Janssen to talk about the about further constraints from semi-classical gravitational path integral. There you go. Thanks. There you have the clicker. And the pointer.
Is working? Good. All right. So first of all, thanks a lot for giving me the opportunity to talk. So indeed, I'll be talking about some possible constraints on the late-time universe from semi-classical quantum gravity, and based on a whole series of papers, not only our papers. This goes back many years, back even until the 70s, as Victor mentioned. So let's start by, again, Victor gave already some motivation, but let's start by repeating again the grand motivation. And the motivation is very grand indeed. We're looking for nothing less than a theory of initial conditions for cosmology. So here I took a plot from a textbook on inflation. We have this prototypical picture of a scalar field rolling down. There's this flat phase, as also Victor discussed, and so there's some inflation. And you can imagine this ball, which is the homogeneous field filling the universe, rolling down from either of these two sides. And depending on which side it rolled down from, there will be different observational implications for the universe. So these will be measured in for example, details of the spectrum of the cosmic microwave background that Victor also mentioned. So the big questions here are, for example, why was there inflation in the first place? So we assume there was this period of inflation. What put the field up here or up here, and how do we decide between these two? That goes on to the second question. So is there some kind of measure on the set of this zoo of phenomenological models? You can imagine drawing many of these shapes, and many of them have been proposed in literature with various motivations. Another question is, what is the spatial topology of the universe? Is it closed? Is it some S1 times S2? Or is it is it flat? And so on. So those are the big questions that we'd like to answer. So here as a good, not string theorist, but I'll start with some experimental motivation. So this plot, if you don't know what these two axes are, don't worry, they're just basically, let's say, cosmological data that we infer from this period of inflation. So a period of inflation predicts values for this R and an S. Essentially, you can see them as properties of this cosmic microwave background that we're observing. So these are kind of constraints. You put these are satellites, you put various constraints together, and you see that we're pushed towards these small values of R, which is essentially the prevalence of primordial gravitational waves, and this NS is the so-called deviation from scale invariance of the power spectrum of scalar fluctuations. If you don't know what that is, don't worry. These are observational things that we measure, and we'd like to predict, why we're roughly in this region. This one is very interesting because it signals, again, the existence of primordial gravitational waves. So, okay, now I mentioned this zoo of phenomenological models. So here is part of the zoo. It's all of this green region essentially are various models, and so we have various predictions for them. Here are the models. Doesn't matter. There's a bunch of functional forms for this potential. As I said in the beginning, depending on the shape of the potential, you get a different prediction for these observational parameters. And here are the two things put together. So these models 3, 4, 5, and 7, they seem to be quite good. The other ones seem to be quite bad. Why is that the case? And okay, how should we view this? So to tackle this problem, the point of view that I'll take is that of quantum cosmology. So I'll be quite brief, as Victor already introduced it quite a bit. So we'll consider the quantum state of the universe. So it's some functional that lives on a space-like slice of the universe, a Cauchy slice, which I call sigma. And you have some metric and induced metric on here, and fields phi. So we have we have this state. It's not an arbitrary state. In GR, there are constraints, and physical states, they get annihilated by operator versions of the constraints. One of them is h psi equals 0, the famous Wheeler-DeWitt equation. Okay, so just very briefly, so we roughly psi squared gives you the probability for such a configuration on a space-like slice, and also it's conserved along classical evolution. So if you evolve this h phi forward to a new slice, you get an h I prime and a phi prime, these two probabilities are equal to each other because of this equation. So that's how we think of this. So we assign some probability to an entire history of the universe. And so notice here that the boundary conditions are imposed in principle at late times. I specify these arguments and then I get a probability. But that's roughly equivalent to initial conditions because of this conservation of probability. Okay, so that's how we think of this wave function. Now, how do we compute it? Again, I'll be brief because Victor introduced it. So we think of this psi Hartle-Hawking, which is a specific proposal for the state, which is the one that I'll focus on. We imagine it's generated by a path integral of this type. I had some slides on motivations of this state coming from Euclidean path integral in quantum mechanics, how you can generate the ground state there, or in inflation, we calculate the ground state wave function of fluctuations via a very similar procedure. Of course, there we don't sum over the metric, we just sum over fields, but we do some kind of appropriate contour deformation here, where you go into the complex time plane. Similarly, here, this integral is supposed to be defined by summing over some appropriate set of complex configurations. I won't specify what that is because that's a very difficult question. I'll implicitly get there. But you sum over closed manifolds M in this no boundary proposal. So there's no boundary to the past, but there's just one boundary to the future. You have some closed manifold with a boundary, with one boundary, and so this is the picture that you get. Okay, so now back to this. What exactly are we summing over here? So I said that the exact question is hard to solve. Like there's these typical problems associated with Euclidean quantum gravity, that this Euclideanized version of this path integral wouldn't converge, and so on. So that's a difficult question. But in the late time regime, we imagine where the universe is large and classical, we imagine that it's given by some sum over saddles. So here, this index goes over some classical solution of Einstein's equations on this complex manifold, inducing the right boundary conditions, namely these. And A here, this index class, is some class of smooth metrics and field configurations on this manifold. And the focus of what I want to say and what we did recently is we investigated a proposal for what this class A could be. It's a very specific proposal, and we examined the consequences. So let me try to get to that. First, so this Hartle-Hawking state, just one slide review. Victor mentioned that it's of this form. So if you have some state of the universe which has some size A, so imagine a state at the end of inflation, some huge universe filled with some scalar field at the end of inflation. That was like Victor's red dot. No? So the probability goes like this, where the weight, so this is the phase, the magnitude of the wave function scales like 1 over h star squared. So that's this Euclidean piece. Along that piece, the metric is roughly that of a force sphere. So this is a force sphere with radius 1 over h star. Okay, that's this piece. You glue it onto this Lorentzian, quasi-Lorentzian piece. I say quasi because once you're no longer in exact de Sitter, this is no longer an exactly Euclidean metric, nor is this an exactly Lorentzian one. It's kind of a complex deformation, but it's a small one, so I still draw it like this. And so the metric along the Lorentzian piece, when the universe is growing, is roughly of this form, where this effective de Sitter radius is changing slowly with time. Okay, so then we evolve and we get this big universe with some final age. Okay, so so a recap of the problem here is this gives a rather alarming result because it predicts that this h should be as small as possible, and so you get very little inflation. So that was what Victor was explaining. Another way to say it is that you get a predicted curvature parameter. So this a naught h naught is the scale factor today. Well, we observe this to be very small. There's an upper bound in the order of something like 1 part in 10,000 or so. So this wave function would predict that this parameter should be as large as possible, which is no good. So that's why it doesn't correspond to observations. So I won't be able to solve this problem in any generality, but I'll try to make some possibly a step in the right direction. So here's more of the meat of our work. So it relates to a condition on this class of complex metrics that we should be including in the sum. It's a condition that's due to mathematicians, and Witten, who can probably be counted as a mathematician also. So in a paper which is so an axiomatic quantum field theory paper. So in principle, it has nothing to do with quantum gravity. These two authors, they introduced a class A of complex valued metrics. So the metric, you write it in some coordinates like this. Now here we imagine for the manifold could be a real one, let's say like a ball, like the one that we had for Hartle-Hawking. It's a real space, real coordinates, but you allow the metric components to be complex. And so which class is it? It's one that's defined by by this formula, essentially, where here this is like a partition function for a free p-form gauge field. So we take the simplest possible thing, a free p-form gauge field, we consider its action on this 4 manifold, and then we try to calculate this, this partition function, this path integral, by integrating over overall gauge field configurations. And so here in this action, as you know, I'll show it soon again, but of course there's a bunch of factors of G appearing when you contract the indices on the F. This is a p-form, so you also have a root G, and so there's G's appearing here, but the point is that you would like this integral to converge. So that's the class, and that's a class that defines a class of metrics in some way. And so the idea of these authors, they had a different motivation again, but just to give you the idea here is that they wanted to define, they wanted to give a new axiom for quantum field theory. So their Lorentzian metrics, they lie on the boundary of this space, because for a Lorentzian metric you would get like an oscillatory integral. You would get an I times a real thing. So mathematicians don't like that. They want something absolutely convergent that makes sense to them. So you define this class where these metrics lie on the boundary, so of that space. So this is like you can do a small deformation of a Lorentzian metric and get something that lies in the interior, in the sense that this path integral manifestly converges. And so the idea is that if correlation functions of a QFT are well defined on A, so you put in some operators here, the path integral converges, we can compute them on this class A. Now we can let G, the metrics in this class, these complex valued metrics, we let them go to the boundary. And in that way we can define properly what are Lorentzian correlation functions. So it's like an I epsilon prescription. And their point was that if you have all of this, if your theory is well defined on this class A, then automatically standard QFT causality axiom will be satisfied. So correlators of operators at space-like separated points, they will these will commute given some condition on it. So that was their motivation. So now, okay, so I won't go over too many details. This is kind of what I said. The G's appear, and so it turns out that this whole condition of convergence is actually very simple. So it translates itself into a very simple condition. So it turns out that if those path integrals converge, you can always choose a real basis on the manifold in which G takes a diagonal form. First of all, first statement. Secondly, those coefficients, which are complex, they have to satisfy this condition. So the sum of the absolute values of the arguments have to be smaller than pi, where the argument is defined between minus pi and pi. So, for example, a Euclidean metric has everywhere positive real numbers here. The sum is 0. It's very nice. A Lorentzian one has a single minus sign, so that will give you pi, which is not smaller than pi. So that lies exactly on the boundary. Then you have this whole bunch of complex ones, which either live in the interior or outside. Okay. So now, so Witten proposed that what we were saying. So I called it with the same symbol. So could it be that this class of metrics that we should be summing over in quantum gravity, could it be that those are relevant actually for computing something like the wave function of the universe? Okay. Okay. So that's in short, that's what we did. Okay. So we explored whether these complex Hartle-Hawking metrics that arise in the context of inflation and also in the context of anisotropic cosmologies that I won't be able to talk about, do they obey this condition of being allowed? And the answer is a bit surprising. It's not trivial, so it's not like all are allowed or all are disallowed. Actually, there's a fine line in the middle that makes a non-trivial distinction between what's allowed and not. And it seems like in the context of inflation, this gives you, actually, which is something that it's in agreement with observations. That's interesting. And there's some implications also for the spatial anisotropy that I won't talk about. So here are the bottom line. So remember this plot. We had the zoo of models. We had the observational constraints. So this is what you get. by applying this condition, essentially. So each of these represent a model of inflation. All of these points represent essentially a final configuration of the universe after having gone through some period of inflation. And so we subject those complex metrics that generate this universe to this condition, and we find that these ones in red don't satisfy the condition, while the ones in green do. So it seems to not like that R is too big, and this suggests that there's some kind of theoretical reason for quantum gravity not to want to produce a large R, which is what we seem to observe. This bound is always going down. Okay. Okay. There's some analytic way of capturing this. There was a okay, and the constraints are pretty big. If you look at here, for example, m squared phi squared inflation, which is the simplest model of inflation, you have just a quadratic potential. This is completely ruled out, for example. Just many things are ruled out, but the simplest model is ruled out.
It was already ruled out, there wasn't m squared phi squared.
Excuse me?
I think it was already ruled out a long time ago, wasn't it?
Oh, yeah, sure, by observations, but now theoretically also like just yeah, sure, exactly, yeah. No, it's already outside of observation. Okay, so let me probably finish here. Yeah, there were some things. Just let me say what are the open questions. So one of them is still what solves this large curvature problem. This condition on complex metrics addresses part of it, but not all of it. So I didn't have time to go into that, but definitely doesn't solve the whole problem. Perhaps we need to consider another quantum state. Perhaps there are wormhole contributions, like the one that Victor was talking about. The second big question is, when exactly should we be applying this criterion? Should it always apply, or perhaps we can allow some tachyonic mode, which is one of the conditions essentially. Maybe we can tolerate one of the conditions being not allowed for some time, and maybe that's still okay. So we need to think about a bit more for when exactly we should be applying all this. So thanks, that's it.
Questions?
So I myself haven't verified this, but there are claims in the literature that this double cone geometry doesn't satisfy KSW.
Yeah, that's right. Yeah.
But does Victor's wormholes, bracket wormhole, also doesn't satisfy?
It also doesn't. Yeah. So that's part of this number 2, I guess. So to understand really physically, I guess, a bit better. When does this condition make sense? Although there was a paper by Alex Maloney and collaborators who discussed generalizations of this double cone recently, and they exactly used the criterion to rule out like part of these double cone generalizations and to keep others, and they do seem to find that it makes sense. So, okay, but this is also something I need to. It's a good question. So that belongs to number 2.
Any sort of intuition as to why this KSW condition was suppressing large R models?
Sorry, yes, just to repeat the question. Yes, that's right. Did you have any sort of intuition as to why this KSW condition was suppressing models that give large tensor-to-scalar ratio?
Yeah, good question. So, mathematically what's going on is that H during inflation is so if H were not changing by a lot at all, it would be very close to de Sitter, and that's an allowed geometry because it's Euclidean and then approximately Lorentzian. So if you're very close to that, you're going to be allowed. Now H is changing by a large amount, and essentially what it does is it makes this Hartle-Hawking instanton too complex, and it happens to be in such a way that it pushes you. Yeah, you become too complex, and you're not allowed by the criterion. More than that, really physical intuition that would also belong to point 2. It would which condition that fails is essentially the mass. If you would add a perturbative probe scalar matter on the background, the mass term is changing sign. There's nothing you can do about it. In these geometries, is any way that you want to connect the smooth no boundary origin to the final point, necessarily along any contour you draw, any complexification, the mass term necessarily changes sign. So you cannot avoid a tachyon appearing in this spectrum. But a real intuition, I think that's precisely what's lacking.
Okay, let's thank Oliver again.